Hi everyone, my name is Federico Pozzoli and I'm a master student from the University of Milano Bicocca. My project has the aim to search for a possible gravitational wave background from a cosmic population of EMRI with LISA. In this work, I collaborate with Alberto Cesana, Matteo Bonetti, Nicolaus Carnesis, and Stanislav Babak. So first of all, with extreme mass ratio inspiral, we intend the inspiral of a compact object onto a massive black hole in the center of a galaxy. The typical mass ratio of this relativistic binary ranges between 10 to the minus 9 and 10 to the minus 4. Due to their extreme mass ratio, EMRI will complete thousands of orbits around the massive black hole and inside the LISA sensitivity band. And for that reason, they will be an incredible tool to study the environment surrounding the massive black hole. However, the amplitude of a typical EMRI event is below the level of noise fluctuation in the detector. And therefore, many thousand more of EMRI will be present in the LISA data without meeting the detection threshold, either because they are too far away or they have too many years to go before the final plunge. And so the incoherent piling up of the GW signal emitted by these EMRIs generate a confusion noise. If this signal exceeds the LISA noise power spectral density, in the worst scenario, the detection of other sources would be more complicated. Hence, the need for the characterization of EMRI GWB for the LISA mission. So first of all, we have to generate the catalogs. In order to provide an astrophysical motivated estimate of GWB, I consider the astrophysical model developed by Babak et al. in 2017. This model encompasses a range of plausible prescription for the most relevant ingredients affecting the EMRI formation. For example, from the cosmic evolution of the massive black hole mass function to the relation between the massive black hole mass and the density of the surrounding stellar environment, or again from the rate of EMRI formation given the properties of the galactic nucleus to the occurrence ratio of the direct plunges to EMRIs. The main idea behind these 12 models was to have a range of event rate between over-optimistic and over-pessimistic. In particular, we believe that the model 1 is the most realistic one. To generate the catalog, in particular, we perform for each model a Monte Carlo sampling from the EMRI merger rate. To each event of the catalogs, 14 different parameters will be associated. Each of them affects the GW waveform of the EMRIs. In particular, to complete the list of parameters, I draw randomly the angles theta s and phi s, which are the sky location of EMRI, and theta k, phi k, which are the direction of the spin of the massive black hole. To complete the generation of EMRI catalogs, I had to perform different cuts because two reasons. The first is the computational cost. You can see in the table that the number of sources of the initial sample is extremely high, in particular in the model 12 and 7, and the evaluation of the background would require a huge amount of time. And so I decided to select only the EMRI was contribute to the GWB is more important. To realize it, I compute the signal to noise ratio for all this system, exploiting a simple waveform, which is the analytic kludge, and I select only the sources with SNR greater than 1. The second reason is due to the choice of the waveform. I start to anticipate that I decide to compute the GW signal of EMRI using the Augmented Analytic Kludge, and to avoid the computational issues with such model, I removed the binaries with initial eccentricity bigger than 0.9 and initial semilatus smaller than 10. This cut allows to reduce the number of sources. In the same time, we keep most of the original signal, as you can see from the percentual of total SNR lost. After knowing how to generate the population, we have to choose how to compute the gravitational wave signal. As I said, to generate the waveform as quickly and accurately as possible, I decide to use the Augmented Analytic Kludge with the 5pn trajectory, which is directly encoded in the package called fast EMRI waveform. The Augmented Analytic Kludge is a combination of the analytic and the numerical kludge. The original AAK generates a small section of trajectory with NK, and then maps the AK trajectory to the NK result, and finds out the best fit parameter. Then the final waveform will be generated by AK with these new parameters. To go in more in details, the analytic kludge basically treats the EMRI as a Keplerian binary emitting GW via quadrupolar emission, evolving the parameter of the system through a post-Newtonian equation. Instead, the numerical case compute the orbital evolution directly from the integration of the geodesic equation in Kerr metric. The AK that I use in my analysis is improved with the new 5PN orbits, where the fundamental frequencies are directly computed along the trajectory and convert this to the basis used in the analytic kludge. Another improvement consists in the fact that the orbit is computed till 0.1 of the separatrix, which is the locus of points that separates the bound orbital motion from trajectories that plunge into the black hole. So with this tool, I generate basically the H plus and H cross polarization in time domain, considering 4 years of mission. And then I use the LISA data challenge packages to recover the TDI variables in frequency domain. In particular, I consider the optical combination, and so I mean channel A and channel E. At this point, we have just to calculate the background. I use an algorithm called iterative foreground estimation to remove the detectable source, which is it has been already used with the galactic binaries, and it works as follows. So first of all, it generates the SNR for each EMRI in isolation, which means considering just the instrumental noise. Then it computes the power spectral density by adding to the instrumental noise the running median of the power spectrum of the initial background. And it uses this quantity to evaluate the new SNR ρi. If ρi is greater than the threshold, the source is removed from the noise. To allow for the EMRI complexity of LISA data analysis, previous work assumed that an SNR of 30 would be required for the detection. The grid-based search suggests a threshold of 40, but we believe that we can do better. Indeed, for my analysis, I use a threshold of 20 because it is the lowest SNR EMRI we have managed to detect during the mock LISA data challenge. After removing all the brightest source, the code goes back to point 2 and evaluates the new power spectral noise. The algorithm continues until there are no more sources, resolvable, or when the power spectral density is close to the previous one within a prefixed factor. So with this, I use this program to for all the 12 astrophysical models, and the final results are showed in the picture both for variable A and D. We can clearly see that model 12 and 7 are the most optimistic, and they would be detectable. Instead, model 11 would be negligible for LISA mission. To quantify the detectability of the model background, I compute the total SNR, which are written in the table, together the number of sources which would be detectable in 4 years. In conclusion, this analysis has shown that despite the selection in the samples, some astrophysical models of cosmic population of EMRIs could influence the LISA mission, especially in the high frequency of the LISA band. It would be interesting in the future analysis to include the stellar mass black hole binaries, because we expected that their background could be in the high frequency band as well. And to completeness, we should add also the galactic binaries noise. So thank you everyone for your kind attention.